computer. All right. Okay. Last time, if you remember, we talked about the velocity, and we finished at when the axis of rotation does not pass through your fixed reference frame. And you saw that there was an element extra added, right? It was P minus Q. And so the distance between your body frame and the fixed frame would always change. We put both cases when the axis of rotation goes through the fixed frame and when it does not in matrix format. And you saw that both of them look similar. So the general format looks the same. We have two kind of velocities, well, three if you want to be correct. One, when we have a prismatic action, we only have linear velocity, correct? When we have a rotation happening, we could have two different kind of velocity. If the axis of rotation passes through the fixed reference frame, you only have rotary, the angular velocity. But when it does not, you have the linear motion as well, right? Caused because of this. Any rotation, any angular velocity produces a linear velocity also, right? So when we have linear velocity, we could have a prismatic joint or a rotational joint. When we have angular velocity, for sure we have a rotational joint, right? And if you remember, I think we did go over that as well. No. So this. So this was the review for that. We talked about how to get the differentiation of a rotation matrix. Do you remember R dot B? How do you do that? Talk about it. This is element-wise, right? You find the 3x3 matrix and you get the differentiation of every element. So R dot, basically whatever R is, and then for every single element, we find what the d to dt of that element is. All right. Now, we also know that one of the characteristics of your rotation matrix is that R times R inverse is going to be an identity matrix, right? So we're going to use this to arrive to another expression. So we know that expression. So let's assume we are looking at RSB. So S is your fixed frame, B is your body frame. So RSB multiplied by R inverse. So that T means that the element could change as time passes. So it's the case when you have, for example, rotation, right? So as time passes, your theta angle changes. So the rotation matrix in different time stamp is going to be different. That's what it means. So we can use that. And from before, if you remember, we said that we can write V of S, the velocity in the fixed frame, equal to R dot SB times P of B. We worked on this in the last class. If you don't remember, go check the lecture from Friday. Now, what if I write this? I multiply by identity matrix. Does anything changes? No. So we're trying to prove something. Like whenever you're proving something, you pull these kind of tricks, right? Now, this identity matrix could be anything that's identity, and it could be the expression that we just introduced. So it should not change anything in our result, in our VS, if we multiply that expression into this. So if we open that up, so if I put I, which is this expression in here, then I get R dot SB, RSB inverse, RSB PB. Now, if you look at this, if you remember our cancellation, this is your PS, right? P of S. So you see V of S is equal to a matrix multiplication times P of S. So kind of still following the same thing we said for position. And you know that this expression before P of S is a matrix. Multiplication of two matrices is going to still be a matrix, right? Now, we can prove, and I want you to prove it, and when you check the annotated lecture, the proof is in there, that this RSP, or .SB RSP is a skew symmetric. Meaning that we can write it in this form. So omega is that axis of rotation, right? So I can say then this is equal to yes. So I have Vs is equal to skew symmetric of omega S PS. Omega S is a vector in fixed frame. You can't prove this. If you think about it, you couldn't do it, then when you review and lecture, you will see it's actually very simple, very simple. Now, velocity in fixed frame, V of S, is equal to a skew symmetric representation of an axis in the fixed frame multiplied with the position of that point in the fixed axis. Let me do vector, so you know this is a vector, right? P of S, and we know from a skew symmetric equation that I can say this is cross product. So the velocity, the linear velocity of a point of your body in the fixed frame, it can be written as a unit vector in fixed frame cross product of the position of that. Now, what about, so this is velocity in fixed frame. What about velocity in body frame of the same point? So the velocity of a point in its own frame versus the velocity of that point in the fixed frame, right? Does the magnitude of the velocity changes? So if you're going 2 meters per second, the direction might look different, right? Depending on if the body frame goes against the fixed frame or not. So our reference frame does not have acceleration, it's not inertia, right? It doesn't add to the velocity itself. It's just moving with it. We can write the same expression, similar version for your velocity in the body frame. It should not change. So same thing I can, so this is, what is this? This is VB R BS V of S. Because if you have a vector, you remember in one frame, you can operate and multiply it by the rotation between the two frames and find in the other frame, right? So I'm basically using the same thing we learned before probably. Now, if we don't have RBS, but we have RSP, we can get the inverse of that, right? So this is RSP inverse because it's in the other direction. So I can write this expression and it holds. Now, if we do the same thing and multiply it by an identity matrix, the same thing I did in previous slide, we can get to this. So, would I ask you to prove all of this in the exams? No. You need to know how we got there, yes. So this is for you to understand how we got that, but then whenever we use, just use our final derivation, right? So you should be comfortable with the math part of it to understand it, but all you have to remember is that VB is omega B, a unit vector in body frame, cross product with the position of that point. So omega S and omega B or the coordinate of the same point, because it's the same point. You're just looking at it from two different reference frames. It's the same thing, it doesn't change. So they should also be related, right? So if you have one of them, you should be able to find the other one if you have the rotation matrix. So basically, if you have the rotation matrix between two frames, and if you have one of your points, you know where the other point is. If you have the velocity of one of your points, you know what the velocity of the other one is, and you know the relation between all of them. Now, this is important. So, is the velocity of the same point, but in two different frames. And we call omega s the instantaneous angular velocity in fixed frame. Fixed frame is attached to a corner somewhere that does not move. And omega b is the instantaneous angular velocity in the body frame. So the frame is attached to the body as it moves, right? And we show that with omega b. This always holds. R dot SB inverse is the skew symmetric of a vector in S frame. So this relationship is the skew symmetric. So we can write this. This also holds. If it is in SB, or so if it's backward, you see that it's flipped, right? It's going to be the velocity from the perspective of the Earth. So these two will help you when you are trying to find the velocity with respect to different reference frames. Example, find omega s and omega b. So that's the b frame. We have seen this before on Friday. Now this time we attach the b frame, the body frame, to this point. So this is our point P, and we attach the fixed frame here. So if you remember last class, the S frame was here. We just moved it up. We define where S frame is. So we're defining it there. So that becomes our fixed frame. Now, how do we approach this? We also know what RSP is. RSP is this expression. Well, you could tell it's the rotation around the axis. But in case you didn't catch that, this is your RSP. Now, how do we find omega S and omega B? With all the relations that we had previously. That this is your rotation and this is theta of time. Again, omega b and omega s are the same velocity but seen in two different frames. Because if that's your point P, it doesn't matter where you're looking at, it's moving, it's the same point, right? So how do we find R dot SP? Get the differential of each of these element wise. So this is 0, 0, 0. With respect to t, this doesn't have t, right? They have the I'm going to use a shorthand. So if I had d dt of cosine theta t, I'm going to write it negative theta dot. So this would be negative theta dot sine of theta t, right? So I'm going to write negative theta dot s theta. Again, theta, the angle is the thing that's changing, right? That's our variable. We are in time domain, so we can't get the differentiation with respect to time, but we are looking at the rate of change of our theta, the rotation. That's the action that's happening, right? Now, simply get the differentiation of all of this element-wise, you have R dot SC. Your omega S, if you so you have this, now you have to get the inverse of this original matrix to create our inverse. Then you have to do the multiplication. Once you do that, you will get something like this: theta dot 0, theta dot 0, 0, 0, 0, 0. I'm going to change the color of these two, so to show you that there is a green. Does everybody see that? So this is your symmetric representation of vector omega S. Can somebody tell me what is omega S? Do you remember that we had how to create your symmetric? So you have to go back there and see which element is this one. But these are all 0 on a diagonal. We expect that. These two are the same element on your vector, but opposite sign is the same, but they're 0. So those should be 0. That's the only one that has a value, but it is opposite sign. So it shows that it is a skew symmetric. So this tells us that omega S, that vector must be 0, 0 theta dot. Again, I'm going to write this in a different color. So you see the dot there. Now, I know that this has to be, there should be a direction and a magnitude. How do I show that? Just for our sanity. Do you remember that the direction has to be a unit vector? Right? So if I did this, can I say I have a direction 0, 0, 1, and this is the magnitude. So the magnitude of the velocity in z direction of this theta dot, whatever theta dot is. To what? To the vector itself. Yeah. So just as a review, and I don't remember all the elements, but if you had matrix, if you had a vector A that was A1, A2, A3, to put it in a skew symmetric, you had to do this 0, 0, 0. I think it was negative A3, A3. If I'm not wrong, A2, then negative A1, A1. I think this was the negative. I don't remember all of that. You have to go back and check it out, right? And see what are the values. Got it? Good question. Don't, this might be wrong. I don't remember all the elements, but that's how you get there. Now, we will do the same thing for our omega B. So we found omega S, right? You have two ways to go. You can say, okay, omega B. So you said that this always holds. You can do this. You also know that omega B is RBS omega S, right? So you can write that relationship as well. So you have two ways to go. So we can say similarly, let's say that we are going to do all of this. Omega B would be, you arrive to the same solution, 0, 0. I'm going to write theta dot. Zero, 0, 1, theta dot. Okay, this happened to be the same direction for your velocity. This is your velocity vector, right? So Do you know why this happened? Does this always happen that omega s and omega p always have the same direction? Why did this happen? If you answer that, you'll be good on forward kinematic, I promise you. This is like the reverse engineering of forward kinematic. King. You're pretty quick on these things.
Well, I mean, part of it is the fact that if the direct translation from one frame to the other, there's no difference in terms of rotation of frames. So if you rotate one frame, you're rotating the second
Look at the z-axis of both of them. They're both in the same direction. So they didn't change with respect to each other, right? The rotation of the same point. So you expect that they be rotating in the same direction. Now, sometimes in forward kinematic, one of your joints is rotating around this axis, one is about this axis. Now, it will be rotating about a different direction, which would appear here. Let's say if the z direction of that one was in this direction, was in the y direction, then you will get one in the y direction. And it always holds. We actually use this when we're writing forward kinematic. We say, okay, find the direction of all the axes, create the unit vector, then go from there, because if a joint is rotating theta 1, that's always a variable theta 1, right? So the velocity is going to be theta dot 1 at all times. But what direction? Now remember, all of these are a function of time, right? So theta 1 rotating 5 seconds, the value will be different than 10 seconds. But it's still the same variable here, right? So we fill in those times later, and then that tells you the path the robot is taking. So forward kinematic, will write the equation, and then solve or simulate or animate for your to show us how it moves. You just plug in that. You define t is from 0 to 10 seconds divided by this, like this is the span, and then you plug in, and it will show you that this is the full like that. Because it knows exactly where theta should be at all times. Same for the velocity. Does that make sense? Good. So if this makes sense, then you're all going to be set for forward kinematic. Awesome. Makes me happy. All right. There are a couple. So now for forward kinematic, there are two methods that we're going to use. The first method, we use the exponential coordinates. And this is what your book, if you open your book, you go to forward kinematic, that's what it starts with, POE method. The second method is you create a table, all right? It's a more traditional method. I teach both of them, because I think in some cases, the other method, DH table, Devlin-Hartenberg method is easier. Then it's your option to choose which one. In your book, DH table is an appendix. Right, so the book doesn't, so everything that your book lays down follows the exponential coordinate. At the end, there are similar things, it's just the way you set up your system, your model is a little different. So to understand how to set up for POE method, we need to know what is exponential coordinate of rotation. So I set up the lecture so all of this will be meaningful. So now you will understand, because the velocity of a point P, if a point P is rotating about an axis of omega, we saw that it's going to be omega cross P. Now, if this axis was going through the fixed frame, that's it. If it was offset, we just have PT minus Q. That's the offset, right? Now, do you remember when we started this, we said that if we know P dot is so if we had the equation for first order differential equation, we know what the solution is, right? So this is basically based on that solution. So if that is our velocity, so if we have PT, so if that's our velocity, we know the solution, the position is going to be PT e to the power of the symmetric of omega, because that's our matrix, right? If you remember, so if this is A, the P dot is A times P, that's your differential equation. The solution is PT e to the power of that A times T times the initial position, right? Yes? Okay. If you forgot, if you don't know what I'm talking about, go to lectures from last week. This is really important because we're just going to use this solution. We're never going to say that why are we using e to the power of something, but I already introduced to you why. Because that is the solution of a differential equation. Now, doesn't matter what a matrix is. The skew symmetric of omega is a matrix 3 by 3. So I can write PT into e to the power of omega squared skew symmetric omega t. Now, this is in time domain, right? Again, when you have like the robot moving, what is it actually changing in time? So let's say this is the joint and it's moving. What is it changing? Theta, right? The position. So if it was translation, it would be d of distance. It is function of time, but time here is not our variable. The theta is our variable. So I can do a change of variable just to show, because this p of theta is actually theta of t, right? So I can make that change of variable because it's still changing in time. So I can write p of theta, the position, exponential of theta is e to the power of that times theta p0. Now this, we call it exponential position. The position of the point in the exponential form. Now, we know from before that if you have point P, and if you have a rotation matrix between that point in one frame with respect to another, you can write this relationship for it. P of theta is rotation of like some axis and theta with respect to P0. That's in some fixed frame. All right. So this is the rotation matrix between these two frames. This always holds. Now, if you compare this is PT. Well, I'm going to compare this part. This part is really important. I want you to listen to this. This is P theta. This is P theta. This one is P0. This is P0. If these are equal, what does it mean? This and this have to be equal, right? That is our exponential coordinate. So this gives us rotation matrix about an axis omega with theta angle is equal to exponential of skew symmetric of that same omega times theta. You can bring theta in because that's a number, right? You can bring it in. This is the exponential coordinate. So for every rotation matrix, you will be able to write it in exponential form. We use that to create our forward kinematic because every joint that rotates or moves, you can write a rotation matrix between the current position and the fixed position, right? And once you convert all of them to exponential, you can easily multiply. So starting from one joint, you find all the position with respect to each other, and you multiply, and it will give you forward kinematic, which we'll cover to Wednesday. But this is really important to remember and understand where did this came from. All right. You see that these are all the rotations that pass through your fixed axis because we started with P dot omega cross product of P, correct? So this, you need to remember, this relationship holds whenever your axis of rotation goes through your fixed frame origin. A lot of me saying things and talking, I understand. We will get past through this. All you need to remember and understand is the items that I say is important, where did they came from? And you will be only using that, so don't worry about the rest of it. Now, if you have a case that it doesn't pass through the origin, or if you had different velocities, what cases we have different velocities? So I know you're not like sleep all the time with the arrow. talked about it, right? We talked about robots. Robots are what? Joints and links, right? So links don't move on their own, joints must move. So when we say different velocities, it means that can joints have different velocities? Okay, now what are they? Huh? We said it, yes. It could be a linear, which is prismatic action, or it could be your angular, which also could create a linear motion, right? So our general formula for P dot T, P dot omega will be this, considering everything. Right? Now we should still be able to convert that to spherical coordinates. Because in the same thing, it's just moving different joints. This is how we arrived to this big relationship, and we've seen in last class, it's simply by putting the one on the left side into matrix format. We didn't change anything. You remember when I did that on Friday? Like some memory of what I did on Friday. If not, check Friday's lecture, because you actually will use this part. You have to use this part. This is not like you just see it and forget it. I'm going to put a star here. This one is the linear velocity induced by your angular velocity, is the offset. There's a Q in there, remember? There's P minus Q. This one is from your linear joint or prismatic joint. So this is induced by angular velocity. Putting it in matrix form. So we opened that cross product and made the symmetric version. Differential equation, a big matrix, time and position. We know the solution, right? It's going to be P theta, some matrix times the initial condition. So this, what is this S? This S is that whole big matrix. Now just be careful. This is your book's notation I'm using, but for S, this just is a bracket. This does not mean it's symmetric. This just means the big matrix S from up there, this guy is this. That's basically what it is. So it's a shorthand because e to the power of a matrix inside, like a matrix, like really big. So we introduce a new term for it. So S is not symmetric, it's just a big bracket. Omega, this one is symmetric because we open our cross product. That's the difference. See that? All right. Now, this is exponential coordinates, right? So this is for general case that we could have any kind of joint. Now, if you didn't have any prismatic joint, which element in your big S bracket would be 0? Thank God. If you had only linear velocity, you don't have any rotation, right? So you can easily see, oh, okay, that's going to be 0. I would only have linear velocity. So we call this S screw axis. Have you seen a screw motion? What happens in a screw motion? Have you tried to screw a screwdriver? Use a screwdriver. So what kind of motion do you see happening? So there is a rotation, like a helix, right? There is a rotation about an axis. You also have a going down, right? Translation. So there is a linear velocity and there's a rotation velocity. Same thing that we just observed. So we call this motion screw motion. Does it have to always be like a screwdriver? No. Wherever we have these two motions, we call it screw motion. Now, our screw axis S is combined of two axes. One axis of rotation, the other one axis of linear velocity. So omega has 3 elements, or 6, depending on what it is. And your V is 3, right? X, Y, Z direction. You either, your omega as 1 is a unit vector in cases that you have rotation, or your omega is 0, you don't have rotation. There are two different cases, right? So if omega doesn't exist, there's no rotation, then you're going to have prismatic action. So your V will be a unit vector of some particular prismatic action, right? So there will be a very clear distinction. When you look at your screw axis, you would know what kind of motion is happening for that joint. We will write screw axis for every single joint. Why are we doing all of this thing? Like, why are we creating so many different elements and describing? If I gave you the screw axis of a joint that I didn't know, I didn't tell you what it is. By looking at the numbers in that 6 by 1 vector, are you able to tell me what kind of joint that joint is? You should, right? You look at the first 3 elements, if there is 0, so it's definitely not our joint. Right? And then you wouldn't even know by looking at the other 3 in which direction this prismatic is moving. Make sense? So we're doing that so we can represent and model our robot that is in real world and use that in our program. Because you can't put the robot model in the computer, it doesn't go inside. But we can represent it in vector form, then we understand what that vector means. So all of this is to help us model system. Then we can evaluate what is the system doing, because that's the goal of robotics, right? To anticipate where the robot goes or to command the robot to follow this path. But before that, you need to be able to model it. Yes.
So obviously, I understand that if you have like multiple rotational joints, that you can have some linear motion, just linear motion, and have rotational motions with the joints, right?
Mhm.
But wouldn't it also be possible that you could have rotational motion and linear motion of like another joint, so you could have it with that joint?
Great question. So, great question. Do you remember a few minutes ago, I said we write the screw axis for every single joint? So, if your robot has 6 joints, you're going to write 6 different screw axes. Why? Because we need to model them separately. Because the program doesn't understand these are connected. So you remember why, like when we said that, oh, this shoulder is ball and socket, right? But I asked you to think of it as 3 rotary joints. Now it pays off. So for a ball screw that has 3 degrees of freedom, you have to write 3 screw motion, 3 screw axes in every direction. Then it's easier to model it. Now, how do we know all 3 of them belong to one joint? What can connect them together? Zero link or their origins on the same spot, right? They share the same origin. So the reference frame might be in different direction, but they have the same origin. So the origin of our joints are important when we are writing our forward kinematic. So all of this are to help you to model. So every single thing you're learning is in that direction. Taking the human out of the equation and converting everything to equation. All right. Now, when your screw axis is omega and V, then you can define this bracket S to always be this use symmetric representation of the omega part and just the V 0 and 0. Why this is for 0? Why this is not 1? Because the vector is not a point and the append 0 for vector, right? You're using all the knowledge, so you don't even need to remember these, but you remember everything that we learned over the one. If not, focus on your cheat sheet. You need that. Plus the one from last page. This guy. That also needs to go to your cheat sheet, which is the same thing, bracket S, right? So your S omega is the exponential coordinate of your transformation. How did we bring transformation? You remember to represent one joint moving to another or from one frame to another frame, you could also represent it as a transformation. So we can say every homogeneous transformation is equal to the exponential coordinate of the screw axis. So you learned this before. You did your class participation on this, remember? Now, what we learned today is that the solution of the position of one point from one point to another could be e to the power of bracket s theta, which s is this guy, right? If we had this matrix, we can represent it with this. It should all hold because the motion is created either because of rotation or a translation. S is that rotation and translation, their unit vector. Yes? You're like a little bit. I'm not sure. Okay. What is next? Okay, screw motion. I'm gonna show you. Okay, I'm gonna have a quick question. It's not a class participation, but I want you to use the knowledge you've been exposed to. I'm gonna draw it here. Imagine this is your robot. So this is an R rotation. So it's outside. This is a P. This is another R. And then this is your end effector. End effector. So that's not a joint, just something that's there. Right? If I wanted to write the screw axis for this one, for this side, for this third, what should I write? What would it be in S frame? So this is your S frame. It's all with respect to a fixed frame. So I'm trying to find S3, meaning that trying to find the screw axis of this joint with respect to base frame. Let's say this distance is 2. Also, when I write 2m is 2 meters. This, well, doesn't matter to the extent I'm showing the rotation, it could be in arbitrary position. Oh, yeah, imagine that this is this. So the first 3 elements are the rotation, and these are your linear velocity, right? Good. Yeah. So think of the first 3 elements are the rotation, right? So you need to find the unit vector between these 2 rotations. Can you assign the direction of rotation for both of those, like for R, the R1 and R2, like this one? Can you say that which direction, where is the direction of the axis? It's rotating this way. Yes? What does fixed frame mean? So here. This is the direction of your fixed frame. Does that help? You know, this is the hardest part. Use the knowledge you know everything, but how to use them and where to use them. That's the critical thinking. That's what I'm trying to teach you. Otherwise, everyone can read the book, right? You don't need anything.
So I guess we're just like ascribing an arbitrary value.
Not arbitrary value. You have all the information you need. Do you remember when we talked about when we solved that example that find omega S and omega B like half an hour ago? What did that omega B and omega S look like? It was a vector times some theta dot, right? What was that vector? What did I say that vector is? Represented the direction of the rotation, right? So can you write the same for this joint rotating and you want to know how does it look like from this frame? So this is your omega, this is your fixed frame. You want to know, you want to tell me a unit vector that if I didn't look at this and I only knew this x and y, x, y, and z, I would know which direction that's rotating. Let's do that. Here, everyone, listen up. Forget about this whole thing. I'm glad that I actually wrote it. I don't imagine that I don't know. I just walked in and I didn't look at this. I know where the direction, what the direction of the fixed frame is. All right? C is outside and the rest. You want to give me a vector which represents the direction of the rotation of this. Okay? Once you told me, I should understand which direction that one is. That, what is it? 001. It doesn't rotate about x, it doesn't rotate about y, it's rotating about z. Okay, got it, I know. Right? So you're trying, so this is screw axis. Screw axis represents all the velocity, all the direction of motion of this in the fixed frame. So we took care of the rotation part. Now, this is offset. You also want to tell me this is offset, right? This origin is not passing through this. It's 2 meters in one of the directions. So every time this thing moves, if you get this, so there will be always a V vector in this, right? So if this rotates, so anything that rotates, it will generate, there will be V here. What is this V vector? So you want to tell me this is offset. You want to give me a velocity. What is that? It has to be the velocity at this point. And I showed you it's pointing down. Yes, someone's pointing that looks correct. What was it? Yeah. Well, it's 2. So you're saying the direction times the magnitude. You're correct. 0, 0, 0, -1, 0 times 2, because you're also telling me how much is offset. Remember the Q? The Q is the distance. So you can tell me the direction and also how much is offset. So this V3 is 0, -2, 0, which is 0, -1, 0 times 2, right? So 0, -1, 0. Unit vector, right? Unit vector.
Oh, yes. like beta, does that mean beta dot is always going to be like a unit never distributed?
You have the magnitude to introduce, so when you put this in model, so I'm trying to show you the unit vectors. Now, when you write that, you can put -2 to show me that this is actual velocity is -2. The actual velocity is -2, but I was talking about the direction of the velocity. So that would be the screw axis.
How do we get the negative one, like the direction of?
Where is, so y is, this is positive, this
Yeah.
is down, this is negative. -1 y. In y direction.
Where do we get down? We have the going up the right, right?
So you always find with respect to this point,
Yeah.
it's rotating, but at this point is in negative direction,
Oh,
the velocity in the circle,
okay.
because we are specifically measuring in this point. That's why the distance is also when this is an extension, right, or whatever it is. Right, so my expectation is that you can review the lecture. I did this lecture because this showed me you need to study, all right? The next 2 slides is just kind of wrapping up of the whole thing that I said. My expectation is for Wednesday, review all of this and make sure you understand what happened. Because if you cannot pass through this hump, forward kinematic is going to be a miserable PG. But it shouldn't, because I broke everything in smaller pieces and you build up. So understanding this concept of what S is, forget about all of this. You need to understand what that S is, what omega and detail is. All right. So your quiz password, someone left.